Hi. So I want to start from sharing my screen so that everybody will be on the same page. Just to show you where we are and where we are going. Okay, so here I think gravitational fields, simple, all these motions have been dealt with in a way. And the gravitational field, acceleration due to gravity, escape velocity, parking orbit. We started with equilibrium of forces the last class. We are checking coplanar forces. We got to, I think we got to principle of moment. That was last year. Okay, that was last year. But I think we should quickly check. We have done Newton's law. Been able to do this. So we'll just conclude on this chapter 5 because we've not done condition for equilibrium of rigid bodies. We have not talked about stable, unstable, and neutral equilibrium. We're going to discuss that today. So we are on chapter 5. Okay, so it's fine for us. All right, we'll talk about principle of moment of force, Lami's theorem, how we can triangular law of forces and all of that. Yeah. Okay, so that is what we're going to do today, possibly in a few minutes. All right, so let's start from there. Okay, all right, so we're going to start with equilibrium of forces. When two or more forces act on a body, because I'm not going to write all of that, for you to have, like I said during mathematics class, for you to have attained the proficiency of wanting to write JAM physics, it must have been that you have passed through 3 years of secondary school physics. For some people more, because some of you had attended JAM and you just want to reattempt. Okay, so just pay attention to this. When a body is stable or at rest, or is in a state of uniform motion, after being subjected to two or more forces, then we say that that body is in equilibrium. Okay? The forces can also be said to be in equilibrium if by the time you add all the forces together, of course, their resultants will be zero. Why do we use the word resultant? A force is a vector quantity. And as a vector quantity, you cannot have only their magnitude. You have to consider their magnitude and their direction. All right? So that is the reason why when you have something like this, let me demonstrate something to you. Let's say a box is there. A force is pulling this way, and then another force is pulling this way. So let me call this one F1. Let me call this one F2. These two forces, when added together, they will give you zero. As long as this block is not moving, it's either that it is not moving at all. Of course, in this case, it will not move if you want it to be in a state of uniform motion. Because an object that is not moving is also in the state of uniform motion, so to say. I think I'm having interference.
Suliat Lawal, you are disturbing the class. Mute yourself. Mute your mic.
All right. So we can continue. So when you have these two forces, the two condition is that is either the forces, of course, from what we can see here, they are in opposite direction. And then for us to have that, then it must have been that they are of the same magnitude. All right. And is it because they are of the same magnitude that their resolution will be equal to 0? Most likely no. Most likely no. Because you can have that condition like this. And I'm going to be giving you all these parameters. It will help you, because most times you will think physics is about calculation. Most of them is about knowledge of concept. Once you're able to understand some concept, you may not even bother yourself to calculate. You just go to the answer and pick it. All right. So physics is not about maths, where everything is about calculation. Most times they want to ask a simple knowledge of the understanding of the concepts. And once you know it, you are fine. All right. So in this case now, this is what I want you to know. Okay. I wanted to give you another scenario to this. So let's say like you have something like this. So this one is, let me call this one F1. Let me call this one F2. So you can see that in this case now, F1 and F2, they are not facing the same direction. One is inclined to the horizontal, the other is vertically, horizontal predominantly. But when you want to do resolution of forces, you understand that you are going to either resolve it. You can resolve it to either the horizontal direction. This is resolution parts, where this one will be an inclination at an angle theta. All of this one, then you are able to add manually or directly, as the case may be, knowing fully well that they will be in opposite direction. They will be in opposite direction. Okay. So let me give you an instance. Let me give you an instance. There was a popular question I used to quote verbatim. A mass is under the action of force. One is acting in 5 Newton in the southern direction and 5 Newton in the northern direction. 5 Newton here and then 5 Newton here. So the question is, what is the resultant force? The answer is 0. Resultant force is 0. Oh my God. We need to mute this person.
Root.
Who is that?
Please, you guys, when you're not talking, just mute yourself. Root. I've told you guys all
Ruth,
these
your
things.
speaker is on. Can you mute it? All right. I think she has now.
Root.
Oh.
Mute it. You are muting, you are unmuting. You are muting, you are unmuting. Just make sure that the red line is, yes, it's crossed.
Leave
You
it
are
like
muted
that.
now.
Leave it that way. So you just listening. Okay, that's fine. Okay, so let's quickly move. Like I'm saying here now, I'm saying this one is 0. Why is it 0? If you consider your northern direction as positive, the southern direction has to be negative. So you just say -5 + 5, then you get 0. And at that point, this object will be stable. It will not move sideways, upward, or downward. It will just be there. It will just be there. All right. Now let us talk about the stable, unstable, and neutral equilibrium. What does it mean to have stable equilibrium? What does it mean to have unstable equilibrium? What does it mean to have neutral equilibrium? I'm going to demonstrate stable and unstable equilibrium with a chair. For a chair that is sitting like this, if you sit on this chair, you will be comfortably seated. You will not be afraid of falling down. But if you have a chair that is tilted this way, and they say, come and sit, you two will be looking. One leg of the chair is hanging. Let's say this is the horizontal floor. One leg of the chair is hanging like this, and they say, come and sit on it. You should know that you won't want to sit comfortably, because it is unstable. It's either you fall or you move forward, and they say you must maintain this kind of position. It's not possible. All right. So when you have this one is called stable equilibrium. Let me number it. I call this one 1. 1 is stable equilibrium. 2 is unstable equilibrium. I will go to neutral equilibrium. I want to use another example. Now, let's check this. A funnel, something like this. If you are standing, okay. If you are standing a funnel like this, maybe the one you use to pour petrol or kerosene into your stove or petrol into your car or something, when you have a funnel standing this way, it's an unstable equilibrium. It may manage to stay for a while, and after a little tilt, you will just see that the funnel gives way. But when you have it in this format, this one is stable, because when you tilt it, it will come back to its original position. So let me number it. For stable, this is 1. For unstable, this is 2. All right. Now, what about neutral equilibrium? For neutral equilibrium, I will use 2 objects. I will use funnel first. A funnel that is lying on its side, kind of something like this. Yes. When you push it, the new position it will assume will just be something similar to this. You can't really tell. Another one is a ball, a football. All right. Neutral, not because it will not move around. It will move around, but you can't tell that, okay, this new position is this side, this new, it will just maintain this kind of a thing. So let me number it 3. But most importantly, let's focus on the funnel, because the funnel is making more sense for us. So the number 1 is stable equilibrium, the number 2 is unstable equilibrium, and number 3 is neutral equilibrium. They can ask you what is stable equilibrium. The state of stable equilibrium is the state at which, when an object is displaced slightly, it will return to its original position. That's what we call stable equilibrium. When an object is displaced slightly, it will return to its original position. That is stable equilibrium. Unstable equilibrium is when an object is displaced slightly, it will go and assume another position different from its original position. If you push this funnel that is standing on its smaller end, of course it will fall and it will assume another position. That is unstable equilibrium. All right. Just like I demonstrated for that of the chair, it's unstable equilibrium. The neutral equilibrium is when you displace it slightly, the new position it will assume is not different from the previous position. It would be displaced. Can you see? For first, that is the difference between stable and neutral. For stable equilibrium, when you displace it slightly, it will come back to its original position. But for neutral equilibrium, when you displace it slightly, it will go to a new position. But the difference is that new position will not be different from the previous position in reality, because it's the same assumption of position that it will assume, maybe in another place, but it will still be its original position in another place. It will be displaced. It will not return back to its original position. That is why I'm giving you the example of ball and funnel. So note that. Now, when you have all of these, we now need to do some little calculation around this equilibrium. We need to do some little calculation, and that is where Lami's theorem comes in. So let me give you an instruction or an example here. Let's say you have a bag, and I know a lot of people used to carry a bag a lot. Let me just demonstrate the bag here. This is a bag. Somebody is saying, Ruth, mute yourself. Ruth, watch your device. What's happening? So when you have a bag, I'm coming. Go. I'm coming. I'm coming. Bye-bye. I have a meeting. Excuse me a minute, please. Let me just Lock this up. Okay. Done them. When you have the bag, look at it. Let's say two people are carrying this bag. You have this. One person carries it there. Another person is carrying it here. The bag itself has a weight which is acting vertically downward. Okay. So I can now say we have F1, we have F2, because the bag is being supported by three forces now. F2, and the third one is F3. Okay. Now, if this bag remains stable under the action of these three non-parallel coplanar forces, if the bag remains stable, then we say that the sum total of all these forces is equal to 0. This is what I call a lemma law. I'm going to state it categorically again. You should listen. The first law says that under equilibrium, if a not move, that is, it will be at rest, or that it is in a state of continuous uniform motion. Very important. It will be at rest or in a state of continuous uniform motion. All right. That is a state of equilibrium. Now, the lemma additional, which is more important now than the first one, because this second one is the real law. It says that if an object is in a state of equilibrium, then the total sum of all the forces acting on that object is equal to 0. The total sum or the resolution of all the forces acting on that object is equal to 0. All right. So that is what we are going to check now. I'm going to write it out in the next slide, and I'm going to introduce you to what I call Lami's theorem, and I'm going to demonstrate some things on this too. So let us see this way. Okay, look at this one now. I've just demonstrated for a bag that is being supported. Now, don't forget that when you have something like this, there must be a point of connection between all the forces. So you have theta 1, you have theta 2, you have theta 3. I need you to pay attention to this calculation, very important. Let me clean this. Theta 3, okay, this is fine. Now, this would be my F1, that is, I can label it anyhow, there is no, but I think because I've already used theta, the force must be corresponding to the alternate angle. That's why I'm changing the direction. So this will now be F2, second force, and then this will be F3. So there are two things I'm going to be demonstrating here now. So we have assumed that sum total, I'm using mathematical notation for sum total, which is sigma. But because mathematics and physics are brothers and sisters, so they share most of this notation. Sum total of all the forces, I call it Fx, where x represents 1, 2, 3. Sum total of all the forces must be equal to 0. That is F1 plus F2 plus F3 is equal to 0. But one thing you should note is that this plus that I'm using does not mean normal plus. So it means resolution. All right. Don't forget that the forces are vectors. So you don't add vectors the way you had ordinary scalar quantities. So addition of vector must follow a resolution path. All right. So that's why I decided to put those arrow on them to show that the forces are vectors. So you don't just add, because when you see F1, F2, F3, and you see one is 13, one is 12, one is 5, you just say 13 plus 12 plus 5, and then you get 30. I mean, it doesn't work that way. You have to resolve it using vectorial notation. All right, that is that. And then in this case, I want to now introduce what I call Lami's theorem. What is Lami's theorem? Lami's theorem states that, maybe should I do Lami's theorem first? Let me use this law. Let me introduce you because it's part of what I want to do. Triangular law of forces. Triangular law of forces before I get to Lami's theorem. So I will now compress the two together. Triangular law of forces states that when three forces, because we are talking about triangle, acts on an object and that object is in equilibrium, then those forces can be represented in magnitude and direction by these corresponding sides of a triangle taken in order. I will come again. If three forces act on an object and that body is in equilibrium, then we are saying that those forces can be represented in magnitude and direction by the adjacent sides of a triangle taken in order. I want to demonstrate it. This F1, F2, F3, I can actually use it to represent the sides of a triangle without any loss of direction. What do I mean? Look at this. F1 is facing vertically downwards. I can demonstrate it. I believe everybody is saying that. That's F1. All right. F2. Oh, let me just, because I'm not going to get the best from here. Okay, so if you are, okay, nice one. Let me put it here. This is F1. Then F2 is facing this direction. Then F3 is facing this direction. I've just formed a triangle. So F1, F2, F3. This is what we call triangular law of forces. You should learn to do this. I've seen questions like this in JAM, that they will give you this. From here, let me use a red pen. From here, Once you have this, it is called triangular law of forces. Triangular law of forces. It says that when three forces are acting on an object and that object is in equilibrium under the action of the three forces, then we can actually represent it in form of triangle this way. So this is one of the things. But Lami, now I've done three things on this place now, on this very page. Now let's go back to Lami's theorem. And I'm going to give you some things to work with. So we have had this, and this. It doesn't matter, it must be always this. It can be in different formats. All right. So theta, let me call this one F1 now. I want to change it. So this one is theta 1. Let me call this one F2. This is theta 2. And then let me call this one F3. All right. And this is theta 3. Lami's theorem says that once you have this, you can actually use sine rule. And don't forget that each of these angles are obtuse angles. They are beyond 90 degrees. All right. It doesn't matter whether it's obtuse. Lami's theorem says you can use sine rule. F1 over sine theta 1. That is Lami's theorem I'm bringing up. I just want to compress it to a mathematical formula. F1 over sine theta 1 is equal to F2 over sine theta 2, and that will be equal to F3 over sine theta 3. This is what we call Lami's theorem. Lami's theorem says that If an object is in equilibrium under the action of three non-parallel coplanar forces, then the ratio of that force to the sine of its angle is a constant. That's all. That's all. So once you remember sine rule, you can work on this. But the only caution is that under sine rule, you have to compress all your angles to acute angles. But here you don't need to. Just use those angles as they are given. You don't need to. However, there are other situations in which if you want to convert this to triangle, you have to balance the angles. Because in a triangle, all angles has to be less than 90 degrees. All angles is either less or equal to, of course, if one of the angles is already equal to 90 degrees, then you should know the others will be acute by default. Because the sum total of angle in a triangle is 180. And what you are having here is 360. So you need to learn how to balance triangle very well. That is mathematical aspect of the physics you need to learn. It's the mathematical aspect of the physics you need to learn. I don't know. Maybe I should give you some work to do, especially about balancing the triangle. Let me give you something like this. Who can give me a better? You pick which one is the right. Which one is the right? Okay, let me use this. So I have this, I have this, and I have this. Okay, so let me say this is okay, F1, F2, F3. All right. So I'm going to give maybe 2 or 3 diagrams. You tell me which one is the correct one. Tell me which one is the correct one. Let me give you something like this. Okay. Okay. No. Let me give you something like this. Okay. Let me give you something like this. I'm going to label each of them. Okay. Yeah, I can actually do that. Okay. So let me label. Jan will not give you more than 4 options. Let me use blue. So let me call this one A. Let me call this one B. Let me call this one C. Let me call this one D. I'm coming. I'm checking to see. Okay, so it's not yet done. Just one more thing I want to add. Of course, this one will go like this. Go away. This one will go like this. So I can have this. I can have this, and I can have this. 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 I can have this, and I can have this, and I can have this. I can have this, and I can have this. Okay, so who can give me the correct option? The correct option to all of this. Which one is the correct representative of the above diagram? from the list I have here, A, B, C, D. You can send your answers in the chat. Let me check from the chat. Okay, somebody has sent something. Okay. Which one is the correct option? Somebody said, okay. Who else want to try?
D.
C.
D.
D, okay. D. D. We have about 5 to 6, how many? 5 people. 2 people responded. And they picked the same answer. Does that mean that nobody is thinking differently, or you think everything they said is the correct thing? Okay. Maybe we should not. Okay, I have seen 2 responses. DD. Oh, nice one. So it means everybody is actually flowing well. The correct answer is D. Yeah. Let's not just waste time flogging dead horse. This is the correct one. You will see that the direction here is preserved, which is the same thing as this one. The direction here is preserved, which is the same thing as this one. So the reason why it's correct is because this F1 is facing backwards here, and that is opposite direction. So this is not correct. A and B, obviously, they don't represent. All right. So please note that the correct answer should be D. You have to preserve the direction of the forces. They must not be in any way truncated. And you should try your best to know how to do these arrangements. It's very interesting. Like I said, everything in physics is not calculation. So you have to learn to make sure that you get these properties properly. Okay. And I think I've been able to, I'm looking, please go to your past questions. Because of my condition here, I can't solve past question now. Maybe I will look at questions against next class. Mr. Jatu, I want to believe that we have about 3, 4 or 5 minutes left.
You have less than 5 minutes left.
Less than 5, okay. So I won't shoot beyond the normal of this thing. If you have questions, let me hear from you guys. Let me hear from you guys. Let me stop here. We've been able to do several things under. Okay, let me give you an hint while you are thinking of what to ask. Please note that there are 2 conditions that you need to satisfy for stability of objects. Stability, we are talking about stable, unstable, and neutral objects. There are 2 conditions you need to consider for stability of object. This is a bonus for you. Number 1, the center of gravity must be low. The center of gravity must be low. I will explain what I meant by that. And then it must have a large base area. The center of gravity must be low, and it must have a large base area. That is why you see sport cars, very small cars, sports cars. And those cars that are used for racing, they are very smart, they are very flat, because they run. So that part of the thing that makes them stable is that they are very low to the ground. Center of gravity, very low. So they can run very fast, and then after that, when they apply brake, they will just swirl, and then they will be stable. But imagine trailer carrying heavy load, something like this, and then you have these tires, kind of, don't mind my drawing, This is the center of gravity, carrying heavy load, cannot run the way a sports car will run, because once it pressed brake, calamity will occur. So you can see the center of gravity is very high, but for a car, the center is very low. All right. That is why when you build a house, tall story building, you know, and then maybe thunder strike them and the whole thing will just like that. So be careful. These are for future engineers. To ascertain the center of gravity of an object, the center of gravity must be low. It must have a large base area. I want to stop here for today. All right. So hopefully next class we are going to have questions to practice with, and then we are going to get concepts right, and then we'll move ahead to the next topic. Thank you for today. Do I see a question? I doubt. Nobody's asking. Okay, it's fine. It's fine. See you next class.